Hello everyone. I just want to make this additional video to talk about a few things that I think we need more understanding of. So let me give you a few functions. So we usually express y equals to fx to denote the raw function, and then single prime to denote the first derivative, and then double prime to denote the second derivative, right? So that's what we have. And for example, it can be as simple as x squared, right? So what this means is that the raw function is looking something like this. So let me draw it out. Then it's going to be something like this. So the first derivative is going to be 2x, and then the second derivative is going to be 2, right? So this is something we can do. Now, what this means is that we actually want you to sort of understand what it means. So both the functions, the first derivative and the second derivative, are derived, right, from the raw function. So these are totally derived. And that's actually something special about the calculus, right? So calculus means that we have these additional tools, additional functions to help us understand the raw function, right? So now the question is, in which way, right? How can we understand? How can they help us understand the raw function? Now, the first one, the first derivative, helps understand in terms of directionality, right? So directionality. So for example, that's something we know already. So if the first derivative is positive, then y is increasing, right? Negative, then it's decreasing. So that's something we know. Basically, the first derivative tells us the direction of travel, right? It's increasing or decreasing, right? Based on the slope, the sign of the slope, right? So this is a slope. Now with this, we also know about something about local extrema, right? So that's sort of like another offering, right? Because we know the positive and the negative already, right? So in terms of whether it's increasing or decreasing, then so if we have a point on the left is increasing, on the right is decreasing, then this is a point of local maximum, right? Similarly, local minimum. So that's how we can find the this maximum minimum without using the second derivative, right? So again, we can also use the second derivative, but without using the second, we can also do this, right? By just analyzing the directionality of the function. Okay, so now the second derivative measures or talks about concavity, right? Concavity means that now this is strictly positive, right? Strictly positive means that it's always convex. It's always like this, right? So means the raw function, which talk about the raw function again. So concavity of y, right? So of the raw function, which is everywhere. So it means if we take this point, it's going to be convex. This point is convex. This point is convex. So anywhere, any point is convex, right? So so that's what's about the concavity. Now I want you to know something that it also talks about the first derivative, right? Because literally now, what is a derivative? Derivative is about rates of change, right? Rate of change of the raw function. So now in the context of the double prime, the second derivative, now it's about the rate of change of y prime, right? Because the second derivative is just another derivative of the first derivative, right? So now means that this is talks about or studies the y prime, the first derivative, in terms of the rate of change, right? Rate of change. So that's another level of study. So it actually talks about y. It also talks about y prime, right? So what does that mean? So if y double prime, which is second derivative, is positive, then y prime is increasing, right? Then if it's negative, then y prime is decreasing. So that's the literal sort of interpretation of the derivative or different derivatives, right? So that's something that I want you to appreciate. So they both talking about different things. So if you were talking about second derivative, right, then it's talking about concavity or either the first derivative is increasing or decreasing. But it talks nothing about the raw function in terms of the directionality, right? So for example, in this case, it's all positive, but the function is the raw function is first decreasing, then increasing, right? So even if everywhere else, everywhere across the domain is a positive second derivative, but the raw function y is decreasing and increasing, right? Because it only studies the concavity of the raw function, right? And then who studies the directionality of the raw function? That is the first derivative, right? First derivative tells me that the function is increasing or decreasing. So their sort of objective is different, right? So that's something we need to make sure we understand. Okay, now let me draw one sample curve, and then let's study the function. So if I have this function that looks like this form, and naturally, okay, there are a few things. So okay, maybe the course is here. So first, we can have the intercepts, right? This is something easy we can do. So if we were asked to draw the function, then this is the point you will start with, which is about the raw function. And of course, next kind of interesting point will be the local maximum minimum, right? So how to get its points? We set the first derivative 0, right? Give us a few candidates. Then we use the sidechain method to verify if it's, for example, if this point is increasing on the left, decreasing on the right, then it's a maximum points, right? And also can use the second derivative. Now, the third interesting point is the inflection point. So this is the inflection point, right? So how do we know? Because we also look at this point if the double prime is 0, right? So that's how we find the candidate for the inflection point. And after we have the candidates, we also need to verify if there's a sign change, right? So on the left, so let me draw a separating curve. So on the left, we have y double prime is negative, right? It's concave. On the right, double prime is positive, it's convex. So which makes us which gives us a conclusion that this point is indeed an inflection point. And of course, also you can graphically tell it, right? So, okay, now what this means is that everywhere on this range, right? So this range, everywhere on the left of the separating line, it should be negative, right? It should be concave. And although it is first increasing then decreasing, right? On the right is the second derivative is always positive, means it should be always convex, right? Although it's decreasing, then increasing. Okay, so how do we know it's decreasing, increasing? Then that's where first derivative comes in. So different levels of derivatives tells us different things, and we need to take all this into consideration when we draw the graph. For example, this particular point, we need to make sure it is sort of reflected here in terms of serving as an inflection point. These are local maximum minimum. This is something we usually work with the first derivative. Okay, so I think that's about it. That's just a few things I want you to pay attention to. All right, that's it for this video, and thank you.